Beidler. I'm just starting my 5th year at the Physics Department. And a little caveat before I start, I don't actually do high energy research. Personally, what I do, theoretical fusion theory. So that's trying to get energy out of smacking little things together. There's a lot of physics that's similar, but the Higgs Boson is definitely out of my realm, but I'll do my best not to confuse myself. And hopefully we can have a great talk tonight. So before I actually start with everything, I have a couple of people to thank. Namely my advisor, Paul Kasich, who's sitting over there. He's probably going to hide. But then also another one of the professors from the physics department, Arthur Weldon. They were a great resource for getting a lot of the content for this talk. So they deserve a lot of thanks, along with the organizers who helped me set this up, people who helped me get the presentation going, namely Dia, Aniketa, and Chris. They helped me a lot with setting up the presentation and hopefully giving you something that you can understand. And awesome. So, the Higgs Boson. There's a lot of fuss about it. You probably heard about it. They announced a finding from CERN, which is this big experimental lab over in the Switzerland, France area of Europe, on July 4th of this year. Just to remind you of some of the fuss, I have a couple of headline articles. First one from BBC is Physicists Near to a Key Clue to the Universe. From CNN, scientists edge closer to providing existence of these elusive particle. And I'll talk about this a little later, but that's one of the massive detectors that they use for this huge experiment. And another headline, new subatomic particle, maybe physicists missing link. And right here's what a computer generated graphic of what one of these collisions look like at this experiment. And you can see it's very complex. There's a lot of things going in and out. And hopefully I'll be able to give you guys a little intuition of what's going on. So first off, what is the fuss about the Higgs Boson? What this work does and what these findings do is verify the theory of why some of the particles have mass. So why do we have mass? Why are we massive things? Just to refresh everyone with what mass is, it's a measure of resistance to a change in motion. So imagine that you're throwing something, a baseball per se. It's pretty easy to throw, and it doesn't have any tension on your arm, or too much tension on your arm. Then imagine trying to throw a brick. We know from experience that a brick is a lot heavier, a lot more massive. If you're trying to throw that brick, it's going to be a lot harder than to throw that lighter baseball with less mass. And a consequence of not having the Higgs means none of us would have mass. We won't be able to make the complex molecules and like different things that make us up. So without things having mass, we wouldn't be around. Moving on, you might have heard of the Higgs boson being referred to as the God particle. Actually, that's a misnomer. Excuse my French, but it was actually known as the goddamn particle. So when they're shooting all these little, so as I'll talk about later, they jam particles together and a lot of things come out. And to see this Higgs was pretty difficult. So Leon Letterman called it the goddamn particle back when they started a lot of research on it. So it was very hard to isolate. There was a large background of other events that were covering up to be able to see this. And looks like I missed something at the end, but it was just talking about there's multiple people who discovered this at once. The main guy, his name is Peter Higgs, and the field and the particle is now named after him, but there was also a group of 5 other people who came up with the same theory in the same year. Excuse myself, I didn't say they found the Higgs, but they went through the theory and predicted that it would be there. And that was back in 1964, I believe, when they actually did all this. And this is a picture from over in Germany. I was lucky enough this summer, so 2 months ago, to be invited to the Lindau Nobel Laureate meeting. And it's a meeting of young scientists and Nobel laureates, and it was a week of sitting around talking about interesting physics. And during this conference, we were lucky enough for the Higgs boson to have been found, or a Higgs-like particle is what they call it, that was found. So down here we have 4 Nobel laureates. That is David Gross, he did things on the strong theory. Martinus Veltman, he did things on weak theory, along with Carlo Rubbia. And then this is, I can't think of his name at the moment, but I know that was George Smoot. And he was on the Big Bang Theory. If anyone recognized him from there, he did a lot of things with dark energy and dark matter. And these guys right here, the best people in physics, are talking to the people from CERN at a teleconference at this meeting. So it was amazing to sit here and watch history happen and hear the people who have been involved in making history for years and years talk about it and talk how great of a thing this was and how it really confirms a lot of things. But how did they confirm it? Here's the massive experiment that they use. It's called the Large Hadron Collider. It's also referred to as the LHC, so I'm going to use that a lot, so I don't have to say Large Hadron Collider 50,000 times. But you'll see it's pretty big. This is the biggest experiment that we've built yet, and also the most costly. The experiment was so big, one country couldn't contain it. It actually goes in between Switzerland and France. Most people know it's at Geneva. But an amazing thing how precise this experiment is, there's a train that runs somewhere south of here, and they can actually pick up the seismic movement of the train by looking at how these particles collide just slightly differently. So it's amazingly precise, amazingly big. One loop around it is 16 miles, or 17 miles, I'm sorry. So it's a big loop. And these particles go around this loop a couple thousand times a second. It's pretty amazing. Speaking of how fast they go, protons, so little things they jam together, get to 99.9999991% of the speed of light. So if anyone's familiar with it, the speed of light is what the speed limit. It's as fast as anything can go in the universe. And we're getting particles that are going really, really close to that. So they're really, really energetic, and we sling them together and see what happens. So now that I've given you a little introduction, what do I really want to talk about? I want to talk about what the Higgs boson is and why it matters for this thing called the Standard Model. I want to show you how they found it. They call it the goddamn particle, so it's really frustrating to find. So there's there's quite a bit that goes into actually finding this particle. And then moving on to the future, now that we found this Higgs, this astounding discovery, what is next? Is there something next? And like I say down here, we've really only seen the tip of the iceberg when it comes to all this physics. So I'll start off with the Standard Model and how the Higgs boson completes it. Before I can get to that though, I want to talk about all the forces around us. All the things that happen in our daily lives, a lot of the things that we don't even see, they're all described by 4 forces. They describe everything in nature. Sorry, I went backwards. The first one, gravity. Right here's a picture of Isaac Newton with an apple falling on his head. Things fall, or mass likes to attract itself. So apples fall from the sky to the ground. We have electromagnetism. And this is kind of an interesting one because back in the 19th century, it wasn't electromagnetism. It was electricity and magnetism. And similar to what they're trying to do with all these forces now, in the 19th century, they found out that those were actually one force. And it really dictates how charged particles move around. Next is the strong force. So inside all the molecules that we interact with every day, there's a bunch of atoms. The atoms have a nucleus that's positively charged. From electromagnetism, we know that like charges repel each other. So there's a bunch of positive charges in this nucleus, and we would think they would fly away. But there's this real strong shortwave force called the strong force that holds everything in the nucleus together. And the last of the 4 forces is the weak force. This one's a little harder to explain, but whenever you have some type of radioactive decay, there's a weak process going on. So that's where the weak really comes in. So that leads us to the Standard Model. Looking at just 3 of those forces, so electromagnetism, strong and weak, those combine together, and when we look through the theory, we get a bunch of different particles. This is also called the particle zoo. So now, the main things that we care about are these quarks. These quarks with the U's and downs make protons and electrons, or the ups and downs, I'm sorry. So they're 2 separate things, and you put a couple of them to, neutrons and protons. They make up things in the atoms. They make up the nucleus of atom is just these things, and these are some of their heavier cousins that come into play down the road once we get to higher energies. We also recognize the electron down here, which orbits around the nucleus. So all these things build up atoms. Similar to the quarks, these leptons have some heavier cousins that come into play with higher energies. And you also see over here is these forces. So the forces, all the forces I talked about before, those 4, they have mediating particles. So these forces themselves have to act on particles somehow. And they use these things. So for the electromagnetism, it's what's called a photon. For the strong force, we have the gluon. Then we have the radioactive decay weak force, which you have these Z and W bosons in it. And then right at the middle is this Higgs boson, what everyone's been talking about lately. And in a nutshell, this Higgs allows these 2 force carriers, all these quarks and all these leptons to have mass. Without this Higgs at the center giving mass to everything, nothing would be able to have mass. So quickly, I have a movie from the internet that shows how the Higgs interacts with things, or the Higgs field interacts with things. So you have the Higgs field. You can imagine this Higgs field is on the right, no Higgs field is at the left. Now imagine if we put a photon that comes through, it doesn't have any mass, and it goes at the speed of light, it just flies right through. So, and then when we have the electron come through, there's the photon again. We know the electron has some mass, and when it hits this Higgs field, these particles, the Higgs boson particles, interact with this electron and give it mass. You can imagine, and you see the electron slows down. So the electron interacts with that field and slows down. For a more massive particle, it interacts more with the field, slows it down more, and it gets more mass. A very popular way to look at this, also a nice little analogy, while I get this set up, is imagine that you have a room full of reporters. And then you have two people that walk into the room. One person is just ordinary guy off the street, random person. And then the other person is someone famous. When these people walk through the room, all the reporters are going to walk up to the famous person, ask them questions, take pictures. But the regular person, no one's going to talk to. They're just going to be able to fly through. I should actually put this so I don't give anything away. So the regular person can fly through, while the celebrity gets slowed up by all these reporters. That's similar to the Higgs field. Because the Higgs field interacts with massive particles, it slows them down. But the lighter particles that don't interact with it fly right through at the speed of light. So that's a quick little way to kind of imagine how this Higgs field works. The insides of talking about all of this and being able to describe the Higgs field comes from quantum field theory. And that's it's a marriage of two of the big mechanics that we talk about in physics. The first one is relativistic mechanics. It can easily be described as one word. It's deterministic. If you throw a football or a baseball, you can then go and calculate exactly where it lands, how far it went, how long it's in the air, all these different things, and you know those definitely. But in quantum mechanics, if you throw that same ball, all you can really do is get an idea of what's the probability it's going to land in a certain spot. So if you throw the ball forward, it could land right at your feet, it could land over to the left, over to the right, in the back. Before you throw the ball, you don't know exactly where it's going to hit. It's probabilistic. It's a very interesting abstract concept that takes years to really wrap your head around and understand to the way that these quantum field theorists do. Let's see what's next. So, as I said, quantum field theory is the marriage of these two. Namely that we have some deterministic motions that we can really calculate where things are going, but then also at these small little scales that is probabilistic. If we do things at these small scales a multitude of times, we don't always get the same results. We can only make a good guess at what our result's going to be. So it's a very complex, abstract type of thing. But they do have some math. And to really get an idea of how the Higgs particle comes around and why we have mass, we need to talk about potentials. So imagine that we just have a ball on a hill. We have some weird shaped hill that has a couple of what we'll call them local valleys and local hills. So if you put a ball at A or C and you go and tap on it, try and move it a little bit, it wants to stay at A and C. It's in its lowest potential state at that point. But if you put a ball up at B and give it a little tap one way or the other, it's not going to stay there. It doesn't like to be at a potential hill. Particles and what nature likes to be in these potential valleys. And that has a straight connection to energy. Everything likes to be in its lowest energy state. It doesn't like to be expending a lot of energy. It likes to sit down at A and C and be lazy. So, potentials, everything wants to be lazy. It wants to have as little energy as it possibly can. Now we can take that and we can imagine that now instead of this gravitational potential, that we have some complex potential that has built in the electromagnetic, strong, and weak forces. So instead of the simple little thing that just depends how high you are that tells what your potential is, you have this really complex thing. But I'm going to try and show it in not too complex of a way. So the potential for this Higgs boson and the Higgs field in the standard model, it's symmetric. for its interactions with particles that have mass, namely those weak force mediators that I talked about quickly, the quarks and leptons that make up everything we know. And the form of the potential looks like what is called a Mexican hat. But the main thing about this potential is if in this plane, these two axes that or axes, is what the value of the Higgs field. So the farther you go away from the center here, you actually have a Higgs field. You can see at the very center that we have a potential hill. And you can see at the edges that we also have a potential hill. But that potential valley, where nature likes to be and nature likes to go because it's lazy, it has a non-zero value for the Higgs field and the mass of the Higgs and mass of everything. So because nature has a potential in such a way like this, it needs to have a non-zero mass to be in its lowest energy state. So because nature is lazy, it goes to its lowest energy state. And another interesting thing about this potential is that it's symmetric. So if you would start at the center and spin all the way around, as you look out, the potential is always the same to you. So there's a bunch of lazy points that this ball could go to. It can drop as it has here to the right, it could drop to the left, it could drop in front and back, but it's always going to stay at that lowest potential. And it's an interesting thing, it's called spontaneous symmetry breaking. So nature chooses one specific state. And I don't think Dia brought me the ruler so I could do my awesome analysis. So I'll instead do a little analogy. Imagine that there are 10 of you and your friends sitting around a table, and it's a round table, and you each have a glass of wine, or a glass of this awesome beer here. My favorite's the Stout. Cheers. But instead of everyone having their beer directly in front of them, it's to the side. So everyone has a beer to the left and the right, every single person. So which one do you take? You take the right or the left? Are you going to be rude? Somebody at one point has to break that symmetry. So if one person grabs the left and grabs that beer, everyone else does. If one person grabs the right, everyone does that. So it's a pretty good analogy for this symmetry breaking. And nature does this for us, which is really nice. So nature does it, says here, we break the symmetry, you're in this state, and then once they have that state, or we know this lowest energy state, all these equations that we have from quantum field theory, we solve those equations in terms of this lowest state. And when we solve those equations in terms of this lowest state, we get a couple of new components that come out, these new terms in these equations. And these terms directly apply to these massive particles, the Higgs, all the things that make life what it is with massive particles. So now as an example, I'm going to show you the equation that they actually came up with. That's pretty horrible. That kind of dry heat right there. So it's very complex. There's a lot of different interesting Greek-looking terms, sub and postscripts, and it's crazy. This is actually like 10 equations put together through a bunch of addition in this weird notation. So it's large, it's ugly, and I don't understand it that well. I understand bits and pieces, but what I do understand is where the Higgs comes into play. So every term that what we have a mass, an m, that shows us where we gain mass. So I underlined all the components of this equation that give us mass for massive particles. And then the Higgs, its field, what applies through these other ones, these blue ones. Those should be blue and red, but the colors aren't quite correct. But the main thing is you can see that over a third of this equation is important because of the Higgs. A third of this equation that talks about all this crazy math and how everything works at really, really small scales comes down to the Higgs. So now we have a little idea of why the Higgs is important, where it fits in everything. Now let's see how they really found it, because that's complicated as well. So as I talked about before, they have this massive collider, and we're looking at the LHC. So it accelerates these small particles to nearly the speed of light and smashes them together. And because they're extremely energetic, we know from Einstein, who said that energy and mass is what? I can't find the word. It can convert from one to the other. That if you have a large energy collision, you can create some more massive particles out of it. So even though the protons themselves are pretty light, we can create a Higgs particle which is a little heavier by making these things more energetic and smashing them together. And now, as I had a little earlier, I'm going to show you another internet movie that shows a particle's path, or a couple particles' path at the LHC. So because they can't speed it up, right, it's kind of black, so the red doesn't show up. You can see a particle moving through. Because they can't speed them up to the speed of light right away, they go through a lot of these little feeder loops. So there's actually a bunch of particles in here right now, but they're only showing 2. So they have them through this loop, and then all of a sudden they split them and put them into the main loop. Speed them up more and more and more and more. We'll go around a couple more times. And then they decide to put them into the detector and have them hit each other. And when they smack into each other, because they have this much energy, they create all these extra little particles that fly every which way and fly into the outside of what's called the detector. So there were 2 types of particle interactions that we saw there. The first one was the collision. So we had 2 particles that went around really, really fast and slammed into each other. It's like a car crash. So you get these things going really, really fast, slam them together, and as you know, in a car crash, lots of bits and pieces fly off everywhere. It's like these collisions. You have 2 things that smack into each other, interact, and you can have multiple things get produced. And you can produce some of these really heavy particles. And the thing we saw later, after the particles hit, is what's called or after they hit, you have all these little pieces. Some of these certain particles will decay. It's very similar to what sometimes they call radioactive beta decay. So in carbon dating, you get this radioactive carbon-14. If it undergoes beta decay, it decays into something different. So the main thing here is that we have one particle that started, so in carbon dating it's carbon-14, then it decays into lighter particles. So it decays into this nitrogen-14 and a beta particle. The big thing is we have collisions, smack stuff together, get a lot of things. You have decay, one thing goes out and decays into a bunch of things. Now when it comes to the Higgs, all we're really going to care about at this point is its decays. When it comes to looking at, trying to find a particle or find some interaction, it's all about the decay. So imagine that we have a Higgs boson created after we smack together 2 of these protons at really high speeds. What it's going to do, it's going to go through this weak decay. These are these Z bosons I told you about earlier. And then they're going to further decay into these leptons, so things like electrons. And it decays into 4 electrons. So the Higgs boson, after a couple steps, decays into these electrons. If we have another Higgs boson, it doesn't necessarily have to decay into these leptons. It can go through this other complex. It's actually a strong decay system, and then it decays into 2 photons. So this is where quantum mechanics really comes into the game of quantum field theory. We can have the same Higgs boson, and we only know the chance whether it's going to decay into 4 leptons or if it's going to decay into 2 photons. And that's something they actually see. And it comes into the case of the detector. So at the detector, all those little decay particles slam into the wall. So as you saw in the animation much earlier, all these particles that were created slam out into the wall. And the material in the wall of this detector absorbs the energy from those things. Those things interact with this wall and absorb its energy. It's like on Mythbusters, when they take a gun and they shoot it into that big ballistic jelly. You know the bullet stops, but you can see that jelly really wiggling around. The ballistic jelly absorbed all the energy from that bullet. And then in the same way, the walls of these detectors absorb all the energy of a specific decay event. So if we have one event that happens, we have one collision, everything goes to the walls, we can figure out what the energy of just the decay products of that one event are. And which brings us to the results. So this is what they actually showed on July 4th of this year. On the one side, well, we can see that we have 2 different, what they're called decay channels. One is for this 4 lepton decay, so it had those 4 things that spiked out, and the other one we have the 2 photon decay. First important thing to look at is the axis. So the y-axis is the number of events we got for a specific energy. So on the x-axis is the energy of whatever event we saw. So for each specific energy, as we step up, we see how many times we got an event that had that much energy. And it's the same thing for this gamma, what the gamma plot over here. And interestingly enough, these little bumps that seem so innocuous are actually the verification of this Higgs physics. So what they do in this case on the left, the blue line that you see, and on this case, this yellow line indicate through computer simulations what they expect if there's no Higgs boson. Then the one on the right, this line that juts up, you really can't see it too well, it's usually red. And on this case, the bump that goes up is usually red. That is computer simulation with the Higgs boson in there. And these black dots, the data, is actually how many events they found at a specific energy. So you see that where the black dots line up is also where the theory with the Higgs included lines up. So by looking at this, they verified that there is something there. There's a Higgs-like boson, and it's right around, they call it 125 giga electron volts. So anyone good with prefixes that knows what giga is off the top of their head?
10 to the 9.
10 to the 9?
A billion.
So it's what's
a billion.
A billion. So it's a billion. So it's a billion of these electron volts. So it's what? Yeah. We found something. We found something at a specific mass, and we know some things about it now. And back to the roadmap. Now that we found it, now that we see some of this data, we've talked about some of the theory and understand how it fits in. What's actually next? So we're not actually done yet. There's a lot of interesting things to see past this standard model. So if we go to high enough energies, or we could rather say when the universe was really, really old, when everything was much closer, energy was much more denser at this early universe, we think that these three forces of the standard model, namely the electromagnetism, strong and weak, and also our gravity that we talked about, join up and become not four independent forces, but at these high energies, they're all the same force, which is pretty amazing. It doesn't have to be that simple. I mean, we could even have like 10 distinct forces that do something else, and they wouldn't have to necessarily match all up. But what we think, what we see in the equations, what we see in experiment, is that all these forces should become one super force at some high energy. And how do they actually try and show this? That's string theory. You probably heard of string theory a little bit. Pretty fuzzy for most people who aren't string theorists. But more or less at these very, very small scales, you have these little wriggling strings that are like a symphony of violins playing or something that Brian Green always talks about in the PBS specials. But they're very, very small, very, very high energy, and very, very massive. If you would look at the amount of energy that these strings have compared to some of the particles that we're looking at now, it's around 1,000 trillions up from where we're at now in terms of energy. So to look at some of these things, we're going to have to, it's going to take a while to get up to the energies that we can really probe this layer of the cosmos. And I have a little, making fun of string theory. It's from XKCD, if you recognize it. So the person on the left says, I just had an awesome idea. Suppose all matter and energy is made of tiny, vibrating strings. The person on the right says, okay, what would that imply? And back to the person on the left, I don't know. So string theory, there's still a lot of things we can't test it. It's outside of the realm of the things that we can test right now, but it's somewhere down the road. Hopefully our technology will catch up and we can try and understand everything. That'd be great, right? So to wrap it up, you guys have listened to me enough at this point. So the a Higgs boson, a Higgs-like boson, has been verified at the LHC. And this is really important because it allows particles to have mass. Remember, it's because the universe is lazy and wants to be at low energies, and to be at these lowest energies, we all need to have mass. It was a huge undertaking of physics to find this and verify this. The first thing that Peter Higgs came up with this theory, what, 1964? And now in 2012, we're finally able to verify it. So it's been a while. And to be able to verify it, we've used the largest, most expensive experiment to date. So this is, figure here it's around $10 billion at this point. They're shutting it down now. They got up to what's called 8 tera electron volts, and they're shutting it down for a little while. They're going to ramp it up to 14 tera electron volts. So hopefully they're going to see a few more things, be able to understand the Higgs boson and how it works a little better, just learn more by getting higher energies. What happened to my last point? My last point is basically, there's still a lot to figure out. In every branch of physics, in every branch of science, even inside our own minds, there is so much to figure out still. So never stop looking. Thank you all very much for being here.